everyone, thank you for clicking onto the video. Today's learning objectives are to be able to calculate a value for the equilibrium constant Kc and Kp from experimental data, and to also know the effect of changing temperature on the equilibrium constant for both exothermic and endothermic reactions. So now we're going to discuss how to work out the Kc of a reaction. The simplest Kc calculation questions actually give you the equilibrium quantities already in the question. So the equilibrium quantities are basically how much of everything there is when it is in equilibrium. So calculate the Kc for the following equilibrium given the results of an analysis of the equilibrium mixture, which show that the concentration of SO2 equals 0.230 moles per decimeter cubed, oxygen is 1.370 moles per decimeter cubed, and SO3 is 0.920 moles per decimeter cubed. So what we do is we simply just plug it into the equation. So we have Kc equals x at equilibrium multiplied by x, and then we have A, which is at equilibrium, the concentration of A, and we multiply it by how many moles of it we have, and then we multiply that by the concentration of B, and times it by how many moles of it we have. So if we call this A, this B, and this X, we should be able to find this. So that means we're finding the concentration of SO3 at equilibrium and then multiplying it by 2 because this is the amount of moles of SO3 we have. And then on the bottom we'll have SO2, the concentration of it at equilibrium, and multiply that by how many moles of it we have, and then multiply that by the concentration of oxygen taken at equilibrium, and the moles of that is just 1, so there's no power. So it's really important to remember that Kc measures the ratio with the products at the top, because if you did this fraction the other way around it wouldn't work. So using these values that they've given us for the equilibrium mixture concentrations, we can then work out Kc. So we have 0.920 squared over 0.230 squared times by 1.370, and that gives us 11.7. Now the thing with Kc is that the units of it change depending on the reaction. So the way we work out the units is that we use the formula that we have here, but we cancel out some of the units. So for example, for this example, on the top we have a concentration squared. So we have moles per decimeters cubed squared. And then on the bottom we have another moles per decimeters cubed squared and just a normal moles per decimeters cubed. And so then we cancel. So I know that I can cancel this with this, and then we're just left with 1 over a mole per decimeters cubed. And so the units for this Kc are mole to the minus 1 and then decimeters cubed, because we have 1 over a mole per decimeters cubed. I've also rounded it to 3 significant figures because in the question everything is has been rounded to 3 significant figures. So that's what gives us a clue as to what to round the answer to. Harder questions will require you to find the equilibrium quantities yourself first. So I've bullet pointed how to work out equilibrium quantities. So again, equilibrium quantities are just the moles that we have of each species in the equilibrium mixture, and the question should always give you the starting moles of each species and at least one of the equilibrium moles of either the reactants or the products in equilibrium. So first what you do is write out the equation, and then you write down the initial moles of each species, and then you work out the change in moles for the known species, so the one that you're given the starting moles and the equilibrium moles, and then you determine the change in moles for the other species using the ratio between the known one and the unknown ones. And then we can work out the equilibrium moles of all of them. A really important note is that if the moles of a species has increased on one side, so say the moles of the reactants has increased, that means that the moles of the products will decrease. So we're going to look at this example, telling us to work out the number of moles of each species present at equilibrium for the following reaction, given that we mix 2 moles of A with 1 mole of B, and an equilibrium is established which contains 0.4 moles of B. So the first thing I do is write down the equation. So we have A plus 3B forms 2C plus D. And then I write down the moles that they initially have. So the moles that we've reacted together. So in the question, we have 2 moles of A, and then we have 1 mole of B. And then it doesn't mention C or D, so that means that we assume that they start off as 0. And these are the initial moles. And then what we do is we write down the equilibrium mole that we do know, which is the 0.4 moles of B. So this is equilibrium moles. And then we can work out how many moles have been lost of B during the process to get to equilibrium. And so 1 minus 0.4 is 0.6. So we've lost 0.6 moles of B. So how do we find how many moles we've lost of A? Well, we use the ratio between A and B. So the ratio is 1 to 3. So that means if we've lost 0.6 moles of B, then that means that we've lost 0.2 moles of A. So this would be minus 0.2, and so the equilibrium moles of A would be 1.8. And then you do the same on the other side. However, you need to remember that if the reactants lose moles, then that means that the products will gain moles. And the other way around, if the reactants gain moles, then the products will lose moles. So you do the same thing with the ratios. So now you look at the ratio between B and C. So I can see that I've got a 3 to 2 ratio. So I have a 3 to 2 ratio, and B loses 0.6, and so C should gain 0.4 moles. And with D, it should gain 0.2 moles because it's a 3 to 1 ratio again between B and D. So I gain 0.2 moles, and so C will be 0.4 and D will be 0.2. And now we've found out the equilibrium moles. We can then apply this to finding Kc by converting the moles to concentrations. So now we can find out how to work out the Kc of a reaction without the equilibrium moles. So if we look at this example, 200 grams of ethyl ethanoate and 7 grams of water were refluxed together. At equilibrium, the mixture contained 0.250 moles of ethanoic acid. Calculate Kc for the hydrolysis of ethyl ethanoate. So here we have the equation. So the first thing I'm going to do is work out the original moles of ethyl ethanoate and water. So we have the equation moles equals mass over mR. So we can work out the moles of this. So the moles of CH3COO CH2CH3 is equal to 200 grams divided by its MR, which comes out to be 88, and that's by doing adding up all the separate ARs. So we've got 12 for carbon, 1 for hydrogen, 16 for the oxygens, and that comes out to be 2.27 moles. And then we do the same with water. So we have the moles of water is equal to 7 grams divided by the MR of water, which is 18 because it's 16 plus 2. And that comes out to be 0.389 moles. And so now we can work out the equilibrium moles. So you write out the equation. And then we put in these moles. So we have 2.27 of this one and 0.389 of the water. So this is initial moles. And then we have, we assume that we have 0 of these. Probably 2 3 significant figures because everything else looks like it's in 3 significant figures. And then we put in our known equilibrium mole, which is this 0.250 mole of ethanoic acid. Ethanoic acid is the CH3COOH, so we have 0.250 moles of this. And so now we can begin working out how much we've lost. So here we have gained 0.250 moles. And so that means that looking at the ratio between these two, it's a 1-to-1 ratio, which means that this one must have also increased by 0.250 moles. And then we see that actually the ratio between everything and this ethanoic acid is 1-to-1. So that means that the reactants have both lost 0.250 moles. And so we have that the equilibrium moles are 2.02, 0.139 and 0.250, and these are the equilibrium moles. So then we can use these to now find Kc. Because Kc is just a ratio, that means that we actually don't need to convert the equilibrium moles into concentrations, because if we do that, we'll actually get the same thing. So we can just work out Kc just using the moles. So Kc equals the moles of CH3COOH and CH3CH2OH. So that'll be 0.250 times 0.250. And then we divide that by 2.02 times 0.139. And that comes out to be 0.22. And now we have a look at the units again. So we have moles squared per decimeter to the -6 because we've got 2 of them. And we've got the same on the bottom. So what that means is that they cancel out, and Kc actually has no units for this example. And another thing is that the Kc can be calculated using just the moles because the volumes will be the same, because we work out concentration equals moles over volume. So if we're using the same volume, then that means that all the volumes actually cancel out, because we'll have mole squared over volume squared over mole squared over volume squared. So these two volume squared, if they're the same value, they'll just cancel out. So actually using just the moles for this Kc will be fine. Now we're going to work out the Kp. So for this example, find the value for Kp using these partial pressures. So CH4 is 31.9 kilopascals, water is 31.9 kilopascals, carbon monoxide is 47.8 kilopascals, and hydrogen is 143 kilopascals. So here we have the equation, and now we're going to work out the Kp. So we write out the expression for Kp. So Kp is equal to the partial pressures of the products divided by the partial pressures of the reactants. And so we have the partial pressure of carbon monoxide multiplied by the partial pressure of the hydrogens. And this will be to the power of 3 because we've got 3 moles of hydrogen. And then this is divided by the partial pressure of CH4 and then multiplied by the partial pressure of water. And then this gives us so now we plug in the numbers. So we get 47.8 times by 143 cubed all over 31.9 times 31.9. And this gives us 137,000. And now we need to work out the units of Kp. So like Kc, we write down all the units and then cancel. So on the top, we have a kilopascal for the carbon monoxide, and then we have kilopascal cubed for the hydrogens, and then on the bottom we have 2 kilopascals. And now we can cancel. So we can cancel this, and we're left with kilopascals cubed over kilopascals on the bottom. So that equals kilopascals squared. So the units are kilopascal squared. Now we're going to look at how to find the mole fractions and partial pressures. So first of all, if you've forgotten how to calculate equilibrium moles, then I'd suggest you quickly look back at the Kc videos and find out how to calculate the equilibrium moles before you come back to this video. So after finding the equilibrium moles of all the gases, we use these two equations below to help us find the mole fractions and partial pressures. So first we have the mole fraction of A is equal to the moles of A divided by the total moles of the gas. And the second equation is the partial pressure of A is equal to this mole fraction of A multiplied by the total pressure. A really important note is that the sum of all mole fractions equals 1, and that's because they're all fractions of the total moles of gas, so they have to equal 1. So now we're going to move on to this example. Find the mole fractions and partial pressures of all the gases in this reaction, and the total pressure is given to us as 255 kilopascals. So the first thing we do is work out the mole fractions. And for example, the mole fraction of CH4 would be the moles of CH4 divided by the total moles of gas. And so because we have all the equilibrium moles here, we can actually find out the total moles of gas by adding them all up together. So at the side, you can write total moles of gas, and that equals 0.8 plus 0.8 plus 1.2 plus 3.6, and that gives us 6.40 moles of gas. And so now we can work out the mole fractions. So we have 0.80 divided by 6.40, and that gives us 0.125. And then here we have the same thing. And then here we have 1.20 over 6.40, which equals 0.1875. And then this last one is 3.60 over 6.40, and that equals 0.5625. And so here we have our mole fractions. So now we can work out the partial pressures because they've given us the total pressure here. And so we do the mole fraction times by the total pressure. So we have 0.125 times by 255, and that equals 31.9 kilopascals. Then here we have the same thing, so 0.125 times 255 equals 31.9 kilopascals. And then here we have 0.1875 times by 255, which equals 47.8 kilopascals. And then here we have 0.5625 times 255, which equals 143 kilopascals. And here we have our partial pressures. And I rounded all these to 3 significant figures because this pressure is given to us in 3 significant figures, and also these initial moles that they've given us are also in 3 significant figures. Now we're going to have a look at some questions. So give the units of kp in each case. So we're going to start off with A. And we know that kp is the partial pressure of the products divided by the partial pressures of the reactants. And so we can find out the units quite easily by just writing out the units of each of the species and then cancelling out. So we have the SO3. So let's just say that everything is measured in pascals. So we have a pascal for the SO3. And this is squared because we've got 2 moles of it. And then we have an oxygen, so that's just 1 pascal, and then multiply it by the partial pressure of the SO2, so that'll be pascal squared again because we've got 2 moles of SO2. And so we can cancel out the pascal squared, so we get 1 over pascal, which is pascal to the minus 1. So that's the units for A. And then for B, we do the same thing. So we have the water multiplied by the carbon monoxide, and then over a hydrogen multiplied by carbon dioxide. And as you can see, everything cancels out, so there are no units. And then for C, we have the NO2, which is pascal squared, and then over the N2O4, which is pascal. So the units for the kp is pascal. So this question is slightly different because we're actually given the Kc, but we're told to work out the equilibrium concentration of one of the reactants. So feel free to pause the video and try it out yourself first, or you can follow along. So in the following equilibrium, Kc equals 54.1 at a particular temperature. The equilibrium mixture was found to contain hydrogen at a concentration of 0.480 times 10 to the minus 3 moles per decimeters cubed, and hydrogen iodide at a concentration of 3.53 times 10 to the minus 3 moles per decimeters cubed. A asks us, what is the equilibrium concentration of iodine? And so we don't actually need to work out the equilibrium moles because they've already told us them. So we have 0.480 times 10 to the minus 3 moles per decimeters cubed of hydrogen, and 3.53 times 10 to the minus 3 moles per decimeters cubed of the hydrogen iodide. And so using the Kc equation, we can then work out the equilibrium concentration of I2. So we have that Kc equals the concentration of Hi taken at equilibrium squared divided by the concentration of hydrogen at equilibrium times by the concentration of iodine at equilibrium. And so if we rearrange this formula, then we can find this equilibrium concentration of the iodine. And so the equilibrium concentration of iodine is equal to the concentration of hydrogen iodide squared at equilibrium divided by Kc times by the concentration of hydrogen at equilibrium. And that comes out to be 3.53 times 10 to the minus 3 squared divided by the Kc, which is 54.1, times by 0.480 times 10 to the minus 3. And this comes out to be 4.80 times 10 to the minus 4. And I've also rounded that to 3 significant figures because everything else in the question is. So for B, what effect would doubling the concentration of hydrogen have on the equilibrium position in Kc? So if we have a look at the equation, if we doubled the concentration of hydrogen by Le Chatelier's principle, the equilibrium would move to counteract that change. So try to decrease the concentration of hydrogen. And the way it does that is to produce more products. And so the equilibrium shifts to the right. And the thing to remember about Kc is that it is not affected by concentration. So the Kc remains at 54.1. For C, what effect would increasing the temperature have on the equilibrium and Kc? So when we increase the temperature, the equilibrium acts to decrease the temperature, so it favours an endothermic reaction. So looking at this bit here, it says that the delta H is bigger than 0, which means that the forward reaction is actually endothermic because it's positive. It's got positive enthalpy change. And so that means that when we increase the temperature, the equilibrium will favour the endothermic reaction, which is the forward reaction, and so the equilibrium shifts to the right. And what happens to the Kc is that because the Kc is the ratio of products to reactants with the products on top, that means that if we produce more products, that means that fraction will be a lot bigger. So Kc actually increases. Because Kc is the concentration of products over the concentration of reactants. So if this has increased, the product has increased, that means that this whole fraction will be a lot bigger. So the Kc has increased. Hi everyone, thanks so much for joining this video. We're going to look at some harder questions for the topic of Kp. So number 1 says that a sealed flask containing gases X and Y in the mole ratio 1:3 was maintained at 600 Kelvin until the following equilibrium was established. The partial pressure of Z in the equilibrium mixture was 6 megapascals when the total pressure was 22 megapascals. For A, write an expression for the equilibrium constant Kp for this reaction. So for A, we know that Kp is equal to the partial pressures of the products over the partial pressures of the reactants. And so the expression is the partial pressure of Z, which is squared because there's 2 moles of Z, and then divided by the partial pressure of X multiplied by the partial pressure of Y cubed because there's 3 moles of Y. And so that's our answer for A. And then for B, Calculate the partial pressure of X and the partial pressure of Y in the equilibrium mixture. Okay, so first of all, I'm going to start off with writing out the equation again. Now, it's actually a lot easier than it looks because firstly, you might think that you need to work out the equilibrium moles and the mole fractions in order to get the partial pressure, but actually we can just look at the ratio. And so we're told that the partial pressure of Z in the equilibrium mixture was 6 megapascals. So we've got 6 megapascals of the Z, and this is the partial pressure. And we know that initially the mole ratio was 1 to 3 between X and Y. And so from that, we know that in the mixture at the beginning, a quarter of it was X and 3/4 of it was Y. And from that, we can actually work out their partial pressures. So because we know the total pressure is 22 megapascals, and we've got 6 megapascals here for the partial pressure of Z, we know that all the partial pressures need to add up to 22. And so if we do 22 minus 6, we get 16. So we've got 16 megapascals left to share between the X and the Y. And because we've already been given the ratio of 1 to 3, this ratio carries through the entire way so from the initial, it carries through to the equilibrium moles and then the mole fraction, and then eventually to the partial pressures. So that means that this 16 megapascals is actually shared between X and 3Y in a mole ratio of 1 to 3 as well. And so a quarter of it is X and 3/4 of it is Y. And so if we do 16 divided by 4, this gives us the partial pressure of X because it's a quarter of it. So we have 4 megapascals of X, and then we have 3/4 of Y. So we do 4 times 3, which is equal to 12 megapascals. And that's the partial pressure of Y. And then for C, calculate the value of Kp for this reaction under these conditions and state its units. So now we just plug in all our partial pressure numbers into our expression for Kp. So for C, Kp is equal to the partial pressure of Z squared, so that would be 6 squared, and over the partial pressure of X, which is 4, and then multiplied by the partial pressure of Y, which is 12, and that's cubed. And that comes out to be 5.21 times 10 to the minus 3. And now we need to work out the units. So again, we write out the units separately and then cancel. So we've got megapascal squared on the top, and then we have a megapascal times by a megapascal to the cubed. And so we can start cancelling. So I can cancel 2 off this megapascal and cancel this 1 at the top. So then we're left with 1 over megapascal squared. And so the units are megapascals to the minus 2 because we've got 1 over the megapascals squared. And then for D, when this reaction is carried out at 300 K and a high pressure of 100 megapascals, rather than at 600 Kelvin and 22 megapascals, a higher equilibrium yield of gas Z is obtained. Give 2 reasons why an industrialist is unlikely to choose these reaction conditions. So if we use a very low temperature, that means that basically the rate of reaction is very slow because there's less collisions per unit time, and so it costs quite a lot for the people running the reaction to be able to produce the products. And also for the pressure, if we use a very high pressure, then it's actually quite a big safety issue, and it also does cost a lot. So the answers are that a low temperature is expensive and a high pressure is unsafe and expensive. And for the temperature, you can also put low rate of reaction or slow rate of reaction. Before we move on to the second question, feel free to click off the video and try it for yourself first. So Kc for the equilibrium below is 10 at 450 Kelvin. If 1 mole of the ester is mixed with 5 moles of water and the mixture allowed to reach equilibrium, how many moles of each species will be present at equilibrium? So the first thing I do again is to write out the equation. And then write out the initial moles that we already know. So we know 1 mole of ester is mixed with 5 moles of water. So we have 1 here and 5 here, and then 0 of these two. So these are initial moles. And then we actually don't know. We haven't been told how many equilibrium moles we have of one of the species, so we just have to label it X. So first I'm going to label what we're adding and what we're subtracting. So let's say, well, because the products start off at 0, that means they can't lose moles, they have to gain. So that means on the right hand side we must have pluses. So let's say this is plus X and this is also plus X. That means that the reactants are minus X and minus X because everything is a 1-to-1 ratio. And so we can write out expressions for the equilibrium moles. So we have 1 minus X and 5 minus X, X and X, and these are the equilibrium moles. Now we use the Kc equation to find out what X is. So Kc is equal to the moles of this times by the moles of this over the moles of this times by this. So we would have X times by X over 1 minus X times by 5 minus X. And we know that the Kc is 10, so that all equals 10. And so we form a quadratic equation. So we have X squared equals 10 times by, and this, I'm just going to expand the bracket, so we have 5 minus 6x plus x squared. And then we'll have 9x squared minus 60x plus 50 equals 0. So then we plug that into the quadratic equation. So we get x equals minus b plus or minus b squared minus 4ac over 2a, which is minus 60 plus or minus square root of minus 60 squared minus 4 times 9 times 50 all over 2 times 9. And this gives us x equals 5.69 or x equals 0.976. And now we have to decide which one we use. And so looking back at our equilibrium moles, we can't really have 5.69 because that means that this and this would be negative, and we can't have negative moles So this means that we must have to have x equals 0.976. And so now we found the equilibrium moles of all of the species just by plugging in the x to our expressions. So we have the equilibrium moles. So we have the ester will be equal to 1 minus 0.976, which is 0.024. And then we have water, which is equal to 5 minus 0.976, which is equal to 4.024. And then we have HCOOCH, which will be equal to 0.976. And then also we have the methanol, which will also be 0.976. And those are our equilibrium moles.